we were discussing last time about IIR filters. Now, the design of IIR filters is based on the design of analog filters. Okay. It is a very simple technique. Analog filter design is highly standardized. So, from the specifications you design any of the analog filters and then make a substitution for S a function of Z, okay, or in terms of Z inverse. If you can express S in terms of Z inverse, then you just make a substitution for S, that function of Z, and then that becomes the filter. Now, we shall be taking up some of the simple substitutions that can be made and then see the limitations of different substitutions, and then again we will come back to a little details of analog filter design. Now, as I was mentioning last time, the approximations that we can make are like this. S can be treated as a differentiator or a differentiating element. That means, if I have in the time domain a function x t and corresponding output is y t, then in the transform domain, if I take x s, this is y s, then this element will be s. This was d by dt operator operating on the input x t, giving me an output y t, and this can be used as a multiplier, algebraic multiplier s in the s domain. Okay. So, y by x in the s domain becomes s. Now, in the discrete domain, the same signal, if it is discretized with a regular switching, I call this xn, and in the z domain this is xz and this is correspondingly yz. What is this function? So, whatever appears here, that will be used to substitute for s. This is our primary goal. Now, let us see, when we talk about differentiation, one of the approximations is, as I was mentioning earlier, one of the approximations that we can make, first order approximation, is this difference. This divided by this can be taken as a tangent at this point. That means, the previous value and the increment from the previous value in the function. Okay. So, if sorry, if this is k minus 1 t and if this is t, if this is x k minus 1, if this is x k, then x k minus x k minus 1 by t is a slope of this. All right. So, if I have a curve like this, if I take, okay, so I will come to that later. So, basically the operator s has been replaced by, if I take the z transform of this, what do I get? X z into 1 minus z inverse by t. Okay. So, x z into 1 minus z inverse by t is equivalent to, in the s domain, continuous domain, is equivalent to s times x s. All right. Derivative of x is, in the discrete domain, derivative of x on this. So, we are trying to equate these two quantities. So, leave aside x z, rather if I say y z is the corresponding output, y z is in one case x z into 1 minus z inverse by t, if this product can be taken as the output y, and y s is s times x s in the s domain. So, what we are equating is y by x, the transfer function in the first case, is y minus z inverse by t. In the second case it is S. So, S is 1 minus z inverse by t. This is one substitution. Okay. If I go for the other substitution, that is, if I take the forward value, then it will be x k plus 1 minus x k by t. This will be the corresponding y k, or 1, say this is z times x z, okay, z minus 1 into x z by t is equal to y z, or y by x in the z domain is z minus 1 by t. This is another substitution. This is another approximation. Now, we shall see today some higher order substitutions, okay, and we will see the limitations of these substitutions. Actually, your relationship is e to the power minus s t was z to the minus 1, or z is equal to e to the power s t. This is the actual substitution. If I take log, it will be 1 by t ln z equal to s. So, s is actually 1 by t ln z, and we are making approximations of this kind. Let us see the integration operation. Suppose we take this is a derivative of x, x dot t, and this is t. Okay. So, what will this area under the curve give me? It is x t. Now, if I want to measure between k minus 1th instant to kth instant, this area, okay. So, that is x dot t integral dt integrated between k minus 1 into t to t, this will be this area, and if we approximate it by a straight line here, this is a first order approximation. Okay. If I make a straight line approximation here, what is the area under this curve? It is this plus this divided by 2 into t. Okay. So, it will be x k plus x k minus 1 by 2 into t. Is that all right? Is this okay? It is the area of the trapezium. Okay. So, x dot k plus x dot k minus 1. Okay. X dot k, if I call this as y t, so I can write this as y k plus y k minus 1 by 2 into t. Okay. And that is how much? From the x side, it is slope, yes, x k minus x k minus 1 by, no, x k minus x k minus 1, because what is x k? It is the integration from 0 or minus infinity to this point, area under the entire curve. And what is x k minus 1? Area under the curve up to this point. So, if I subtract one from the other, I get this hatched area. So, it is this difference, all right, which is equal to y k plus y k minus 1 by 2 into t. If I now take z transform on both sides, I get x k will be x z, I get 1 minus z inverse, on this side I get 1 plus z inverse by 2 into t into yz, okay, or y by x in the z domain will be 2 by t into 1 minus z inverse by 1 plus z inverse. Is it all right? So, this is known as bilinear transformation, and this is what? Y by x is what? What is y by x? What is y by x? It is 1 by s. We are performing an integration operation, all right. So, y by x is 1 by s in the s domain. So, this is equivalent to 1 by s. Is that all right? No. Is this okay? What have you done? 1 minus z inverse by 1 plus z inverse into 2 by t is y by x. Y is equal to x dot, all right. So, it should be equal to s, it should be equal to s. So, 2 by t 1 minus z inverse by 1 plus z inverse is equivalent to s, or 1 by s, okay, s is this much. Wherever we find an s, wherever we find an s, we will make a substitution for 2 by t 1 minus z inverse by 1 plus z inverse. Earlier we are making a substitution of 1 minus z inverse by t or z minus 1 by t. So, this is a third approximation, okay. So, like this you can go for higher order substitutions. So, basically you are expressing x k in terms of x k minus 1, all right, and then trying to find out a relation. Suppose we made a straight line approximation here for this curve, all right, and area under the curve was integration of that, okay. Now, suppose we take x dot t, that is y, which is equal to x dot t against t, we make a second order approximation. Say we choose this as the origin. So, y is equal to say a plus b t plus c t square. If you make such a substitution, that means instead of going back by one step expressing the value of the variable at this instant in terms of the previous value, we take previous two values, all right. So, this will now be a part of a parabola, not a straight line. So, if you take these and if we fix our origin here, that is at t equal to 0, y is equal to say y k minus 2, this is k t, this is k minus 1 t, and this is k minus 2 t. So, y k is equal to a plus b into 0 plus c into 0. So, a is equal to y k y k minus 2, y k minus 2 is equal to a, y k minus 1 is equal to a plus b into t plus c into t squared, and y k minus 2 k is equal to a plus b into 2t plus c into 2t squared, okay. So, you can finally get a, b and c in terms of these three values, okay, these three values. yk, yk minus 1, yk minus 2 in terms of this and the t's, alright. So, once you get these, make a substitution, then you find out this area. Once again, that is integration of x dot t, alright. X dot t I have already got in terms of a, b, c, and a, b, c's are already known. So, from there for a second order you can verify for yourself. Xk finally can be written in terms of, I will write only the final answer here, we are not going to get the detailed derivation of all these. So, I will give you t by 12 5 times yk plus 8 times yk minus 1 minus yk minus 2. It can be shown to be of this type. Okay. So, xk minus xk minus 1 will be equal to t by 12 5 yk plus 8 yk minus 1 minus yk minus 2. What you are doing here is, now you will be integrating this from k minus 1 to k and get the area, alright, and that should be equated to yk minus xk minus xk minus 1. So, this is what we have done. So, if I take z transform 1 minus z inverse into xz is equal to t by 12 yz, this side you will get 5 plus 8 z inverse minus z to the power minus 2. Okay. So, yz by xz, yz by xz will be 12 by t, is it all right, 1 minus z inverse by 5 plus 8 z inverse minus z to the power minus 2. This is a second order approximation. You can multiply by z square. So, it will be 12 by t z square minus z divided by 5 z square plus 8 z minus 1. So, this is a second order approximation. So, like that you can go for a cubic parabola. In this a plus bt plus ct square plus dt cubed, you take previous 3 points and once again you get hold of those values of a, b, c, d and then get the expression for the area, all right, and you will get a higher order term. So, this is known as Adams-Moulton relation. Adams-Moulton relation or transformation. So, bilinear transformation is one version of this transformation. Now, what is so good about these transforms compared to the simpler approximations 1 minus z inverse by t. So, let us see e to the power st equal to z. If this is a real transform from z to s, where do I get the imaginary axis of the s plane mapped in the z plane? When I vary s equal to j omega, s is made j omega. So, e to the power j omega t is z, is it not? So, z becomes, and this omega into t is omega, all right. So, this particular line imaginary axis is mapped in the z plane as a unit circle. E to the power j omega is a unit circle, its magnitude is always unity, is it not? So, we are travelling along this with different values of omega here, okay, we are traveling along this. This is 0 to minus infinity, okay, and this is 0 to plus infinity. So, the entire imaginary axis is mapped here on this circle. Is it all right? How many times? Infinite number of times. Whenever I make omega t is equal to pi, I come up to this. That means it is dependent on sampling frequency. Sampling time t will decide how many circles, how often I will make the circles here. All right. So, it is basically mapped as an infinite number of circles ideally. Okay. So, a point on the left hand side of this will be a point inside this, okay, that you can see any point here is minus alpha t plus j beta t. If I make a substitution here, instead of j omega t, s I write e to the power minus alpha t and e to the power j beta t. E to the power minus alpha t will be less than 1, all right. So, it will be inside, it will be a circle like this. If I go along this, it will be a circle like this. So, all the points in the left hand side will be within this unit circle in this substitution. This is actual substitution. Now, let us see our next approximation, one, that is we made 1 minus z inverse by t as equal to s. So, z inverse is 1 minus s t, is that so? So, z is equal to 1 by 1 minus s t. Okay. So, if I make s equal to j omega, so that gives me 1 by 1 minus j omega t. Now, if I now traverse again along this path in the s plane, that means I make omega vary from 0 to infinity or minus infinity to plus infinity. What will be the mapping in the z plane? If you take omega very small, it will be 1, okay. When omega tends to infinity, a very large value, this will be tending to minus j omega t, omega tending to infinity. So, magnitude wise it will be very small, and minus 1 upon j is plus j. So, it will be approaching 0 value from plus j side. So, it will be tangentially approaching 0 like this, is that so? When I go to plus infinity, when I go to minus infinity, similarly it will be like this, okay. So, basically minus infinity to 0 to plus infinity, this will be the circle. How many times it is making the circle? Only once. Earlier the circle was having a center at the origin, and how much was this? 1, this was 1, all right. Now, I am getting a circle like this, well within the original circle. So, this was actually the stable region, but with this approximation I am constrained to believe that this is the stable region, because mapping of the imaginary axis of the s plane is giving me this. So, it is a smaller circle, it is highly pessimistic, very conservative estimate. This point is conceived as an unstable point outside the stable zone, whereas it is not so in reality. It is very much stable, but we are not able to see whether this point is stable or not. We are feeling that it is in the unstable zone, alright. So, the stability is highly conservative, the estimate of the stability of the system is highly conservative. Let us see the other approximation. Any question on this? The next approximation was z minus 1 by t equivalent to s. St is equal to z minus 1 or z is equal to 1 plus st, is that so? So, now if I make s equal to j omega, s equal to j omega, so it is 1 plus j omega t. What is it? Z, when I take this is 1 and it is a straight line imaginary axis. So, this entire region is stable, but actually this is 1, actually the stable region is only this unit circle. So, you are feeling you are safe, you are in the stable zone, but actually you are not so. Actual stable zone is this much. So, it is highly optimistic. Okay. So, this is also not a very correct estimate. Earlier one was pessimistic, but it was guaranteeing stability of the system. This will not guarantee stability of the system. So, let us see what bilinear transform does. Z is now approximated as S is approximated as 2 by t 1 minus z inverse by 1 plus z inverse. Let us see Ts by 2 is equal to 1 minus z inverse by 1 plus z inverse. So, if you make component and dividendo, 1 plus Ts by 2, correct me if I am wrong, if I add 1 minus Ts by 2 is 1 by z inverse. Sorry, is that so? So, that gives me z. So, it is 1 plus j omega t by 2 by 1 minus j omega t by 2, which gives me z. When I make a substitution s equal to j omega, I will get corresponding mapping in the z plane. Okay. So, what is the magnitude? What is the magnitude of this and what is the angle? See, here the angle is tan inverse omega t by 2, here minus of that. So, that will become plus. So, it is twice tan inverse omega t by 2, this is the angle, and magnitude is always 1, it is 1 plus j x 1 minus j x. So, magnitude is always 1. So, this is the value of z, that means it will represent again a unit circle. Magnitude is 1 and the angle is changing. Now, here when I take omega tending to infinity, this will give me pi by 2. 2 into pi by 2, that will be pi. Similarly, from the negative side, if I go to minus omega, so it will come from 0 to minus pi. So, this entire circle will be described only once under bilinear transformation, alright. Whereas, in the actual transformation z is equal to e to the power st, it is making a large number of circling around the origin. Now, it is only a single circle, but so far as the stability of the points are concerned, we are describing the same limits of stability. All right. This is the advantage of bilinear transformation. You do not distort the stable zone. So, we have gone for a substitution like this, S is equal to 1 minus Z inverse into 2 by T 1 plus Z inverse. If I make S equal to j omega on this side, and if I go along a unity circle, if I substitute Z is equal to e to the power j omega, all right, in this substitution, bilinear transformation, I want to see the relationship between the two frequencies. Okay. Ideally omega should be equal to omega into t. Okay. Is that relationship maintained in bilinear transformation, or is there any distortion? So, we would like to see what distortion takes place in this. So, according to our substitution in the frequency domain, discrete frequency domain, Z is equal to e to the power j omega. So, we will make a substitution on this side, and we will make corresponding substitution S equal to j times omega for the continuous domain. We would like to establish a relationship between capital omega and small omega. So, this is the ideal relationship. Since this is an approximation between S and Z, so we would also like to see the transformation what distortion it makes in the frequency domain. So, on this side I get j omega. Z we have made, yes, I can make a substitution here itself. Okay. Yes, we have already calculated that. So, Z is e to the power j omega. Okay. We have already done that, 2 by T 1 minus e to the power minus j omega by 1 plus e to the power minus j omega. So, we saw here e to the power j omega, all right, omega into T j times is equal to 2 into 1 minus e to the power j omega. If I multiply by e to the power minus j omega by 2, it will become e to the power j omega by 2 minus e to the power minus j omega by 2 divided by e to the power j omega by 2 minus e to the power minus j omega by 2, okay, plus. So, this will be sine and this will be cos, there will be 2j term coming out of this, so that j will get cancelled, okay, 2 and 2 will get cancelled. So, this will be 2j sine by cos, so tan omega by 2, okay, or omega t is equal to 2 into tan of omega by 2. This is the relationship between small omega and capital omega. So, if I make a plot of omega and small omega, when omega is small, so it is omega by t by 2 equal to tangent omega by 2, or omega is equal to 2 times tan inverse omega t by 2. Okay. This is what we got earlier also, the same angle. This was nothing but e to the power j omega. So, this small omega j times omega was angle here. So, the small omega is basically this. This is what we have re-derived. Anyway, so this is When omega is very small, this is a small quantity, tan inverse x is tending to x. So, it will be a straight line 2 times x by 2. So, basically omega is equal to just capital omega t. This is the ideal relationship, but when omega tends to infinity, this becomes tan inverse infinity, which is pi by 2. So, after some time it will get saturated. Similarly, on this side. So, when omega tends to infinity, this tends to pi by 2 into 2. So, this will be pi. Similarly, this side it will be minus pi. So, this is known as warping. That means, if I give a signal, say of this much frequency, correspondingly this frequency is compressed. I increase the frequency 5 times, correspondingly there is a slight change in the frequency at the higher level. That means, at the higher level there is a compression of frequencies, all right. At a very low level it is proportional, but at a high level it is distorted. It is distorted in this, say beyond 30 degrees or so, you will find the distortion is quite prominent. So, when we give a specification for any filter, we must ensure that such distortions do not take place. This is known as a warping phenomena. You must have seen in plywoods, they say the top of the table, when it rains or if it gets wet, after some time there will be warping. That means, you are trying to compress the surface. Similarly, here you are trying to compress the frequency. Original frequency is so much, but in the discrete domain you are trying to compress the frequency. So, this is known as warping. So, you have to pre-warp the specification before starting the design. In the analog domain, you stretch it, you stretch this and then give your specifications, design the filter, and then you make a substitution such that after this warping it comes to the normal specification, all right, it meets the normal requirement. So, that is the idea of pre-warping. So, to counter warping phenomena in the design stage, we pre-warp the specifications. So, today we will take up one or two simple analog design and then see after substitution what kind of functions we get. Suppose you are given a specification in the analog domain, we will design the filter in the analog domain and then we will make a substitution like simple bilinear substitution. As I was mentioning the other day, low pass filter for example will be specified in terms of some tolerance in the pass band and something in the stop band. So, this we are referring as, say if it is h magnitude squared, then this was 1 by a square and this was 1 by 1 plus epsilon square. If this magnitude is a squared, then this is how we are specifying the filter. So, 1 by 1 plus epsilon squared will be 1 by 1 plus omega p by omega c to the power 2n. All right. See, a Butterworth filter will be specified. A Butterworth filter is specified in terms of frequency, cutoff frequency omega c, all right. At omega c the gain is 0.707 or h square magnitude will become half, but in the actual specification suppose we do not specify that particular frequency, that frequency is unknown, but I specify some other frequency, call it passband frequency, at which the gain is so much, all right. That means the gain is 1 by 1 plus epsilon squared. Then you have to search for omega p or omega c. Omega c is not given, omega p is given. So this will be the relationship. Similarly, in the stop band I specify 1 by s square. So 1 by s squared is equal to 1 by 1 plus omega s by omega c to the power 2n. Normally we suggest that 1 by 1 plus epsilon square should be, that means this must be at least this much, this gain should be greater than or equal to this much. It can be here, here, above this, but it should not go below this. Okay. Similarly, this should not be above 1 by s square. In the stop band it should be less than, greater than. Should it be 1 by greater than? This should be less than 1 by s square, or 1 by s square should be greater than this. Okay. So it should be well within this and it should be well within this tolerance limit. So if you try to equate these two, so from here I get 1 plus epsilon squared equal to 1 plus omega p by omega c to the power 2n, or epsilon squared is equal to omega p by omega c to the power 2n. Okay. And from here a squared is equal to 1 plus omega s by omega c to the power 2n. So you can eliminate omega c from here. So what I get is a square minus 1 by epsilon squared is equal to omega s by omega p to the power 2n. Omega c gets cancelled, omega c to the power 2n is common, so that will get cancelled. So I will get this. Okay. So from the specifications given you can see if you take log, okay, you can invert it, epsilon squared by s square minus 1 is equal to omega p by omega s to the power 2n, 2n log omega p by omega s, or I could have written this anyway, omega p by omega s is equal to log of epsilon square by s square minus 1. So from there you can calculate n. N, whatever values you get, approximate by the next integer. So take next higher integer, this is the design procedure. Once you have got this higher integer value, then obviously these specifications were inequality specifications. If you equate them, then both cannot be satisfied with the same value of n. Both have been satisfied with a fractional value of n, is not. So substitution of another value of n, approximate value of n, will not satisfy both the equation. Now which one to be satisfied? If you take the second equation, you are solving this at this point at the specified stop band, this value comes within this, but then omega c is, there are two solutions of omega c. See, n has been solved, other things are specified. So, what you are searching for is a solution for omega c. So, there are two possible values depending on in which you are substituting n. So, this will give you some value, this will give you some other value. If we substitute it here, we will get an omega c correspondingly such that it is well within, that is the passband frequency is pushed, omega c will be a little higher, passband frequency will be pushed inside. So, we are very much safe on the passband side. If you make a substitution in the first equation, then it is stop band which will be going further. Okay. So, there is more advantage if we want to, after all we are more interested in the passband restriction. So, we make the second substitution normally and get hold of omega c. Our interest is to find out n and correspondingly omega c. Once you know these two, then your design is complete, because in the Butterworth filter finally we have got H equal to 1 plus omega by omega c to the power 2n. So, n has been solved, omega c has been solved. Once you know these two, H j omega at s equal to j omega, that means omega you make a substitution of s by j, all right. So, this one is obtained from here, I had mentioned it earlier, you make a substitution of omega equal to s by j. So, you get a function of s minus 1 to the power 2n, j square equal to minus 1. So, it is j to the power 2n, which is minus 1 to the power n. Okay. So, if you make a substitution like this, then get hold of the left half plane roots. This will have 2n number of roots, n on the left hand side, n on the right hand side. So, from there you calculate the left hand side roots and correspondingly generate the polynomial. So, you get the filter function. Once you know the filter function, you make a substitution of that s equal to 2 by t 1 minus z inverse by 1 plus z inverse, you get the discrete domain filter. It is very straightforward. So, let us take one simple example of say third order Butterworth filter, all right. That is n is equal to, suppose from here we get n approximately 2.8. So, we will go to the next higher value, n is equal to 3. So, n is equal to 3, suppose n is equal to 3 we get, then n is equal to 3 will give me roots on the, if I take the normalized frequency first, omega c, let us for the time being take, let us take as 1, then 1 plus s to the power 6, 3, 2 into 3, 6 is equal to 0. This is the function you get, s to the power 6, 1 plus s to the power 6, okay, and you find out the roots of this. So, equate this to 0. So, s to the power 6 is minus 1, which means, is that all right? Should it be s to the power plus 1 plus s to the power 6 or minus? It should be minus, is it not? N is equal to 3, so this should be minus. So, for all odd orders, it should be 1 minus s to the power 6. If it is fifth order, 1 minus s to the power 10 and so on. So, s to the power 6 is plus 1. So, a to the power j 2k plus 2k into pi. Okay. So, s will be e to the power j 2k pi by 6 for different values of k. So, k equal to 0, that gives me 1, k equal to 1 2 pi by 6, that is pi by 3. So, e to the power j pi by 3, next e to the power j 2 pi by 3, e to the power j pi, e to the power j 4 pi by 3, sorry, e to the power j, next 5 pi by 3, okay, 1, 2, 3, 4, 5, 6. So, the values are 1, then e to the power j pi by 3 here 60 degrees, e to the power j 2 pi by 3 here, e to the power j pi here, e to the power j 4 pi by 3 and 5 pi by 3. Is that all right? Out of these, you will find they are symmetrically distributed. Left half plane roots are just mirror images of these, and you drop the right half plane roots. Okay. So, because it is h s into h minus s, when I put s equal to j omega, which has given me h j omega magnitude squared, is it not? So, I am trying to find out h s. So, they correspond, since it is a stable system, it is a stable filter. So, the roots are necessarily on the left half plane. So, we take only these roots. So, this will give me correspondingly h s. So, we have taken omega c to be equal to 1. So, you make a substitution now after you have got hold of this. How much is the what is the function corresponding to this set of roots? One is s minus 1 minus minus 1. So, the polynomials will be h s, I will write analog, s minus p 1, which is at minus 1. So, the corresponding factor will be s plus 1. This is minus 0.5 plus j 0.866, root 3 by 2. Similarly, minus 0.5 j minus j 0.866. So, s plus 0.5 plus j root 3 by 2 into s plus 0.5 minus j root 3 by 2, which means 1 by s plus 1 into s squared plus 0.5 into s plus 1. There is no scope for minus signs, all right. Routh-Hurwitz criteria says a polynomial should not have any negative coefficients if it has to be stable. So, in a stable filter you will always get plus terms. So, this is my analog filter. If I make a substitution of s by omega c as a new value of s, then this s I will replace by s by omega c. This was designed with omega c equal to 1. Now, I denormalize it. Okay. So, put in place of s by omega c. So, it will be s by omega c plus 1 into s by omega c plus whole square plus s by omega c plus 1. So, this will be the actual filter, analog filter. And now, we make a substitution 2 by t 1 minus z inverse by 1 plus z inverse, you will get the digital filter. Okay, we will stop here for today, and in the next class we will take up a few analog filter design problems. The next type of filter that we shall be considering is Chebyshev filter. Thank you very much.